Right. Welcome to pre-calculus. We are going to be talking about logarithms today. It's going to take a little bit longer than I had a chance to do in class because I can't see your feedback, so I don't know if it's going to go fast or slow with you guys. It's probably better that I go slow. I'll post this to the face-to-face class too because I probably went a little too far, a little too fast, and pretty much confused everybody. So the things that I want to talk about first is the fact that logarithm is an inverse function to an exponential. Okay, so logarithms are the inverse function to an exponential. Okay, so if you remember what inverse functions do, right? F inverse circle f of x gives you back the original, okay? And f of f inverse of x goes back to the original. So if you want to undo an exponential, you apply a logarithm. If you want to undo a logarithm, you apply an exponential. So if you want to undo, okay, it's a very precise mathematical term there. If you want to undo an exponent, you apply a log. Okay. If you want to undo, can't even spell undo correctly this morning, good word. Okay, if you want to undo a logarithm, you apply exponent. Just like when squares and square roots, right? They have the same relationships. Exponentials and logarithms have the same relationship. All right. So they're inverse functions. If I look at let's go with this one. Okay, if I look at this function, okay, what do I know about it? Well, I know the domain for an exponential function, right? Any x will be just fine. 2 is the base. Okay, the range, right? We only get positive numbers here, so we go from 0 off to infinity. And we have a horizontal asymptote at y equals 0. I'm going to make a little t-table. Okay. So we have x, we have y. Now, how do you make your t-tables, right? We do a -2, -1, 0, 1, 2, 3, maybe. Now, there are more judicious ways of like choosing these numbers, but if you were, if you had to do this in high school for polynomials, for other functions, this is probably your basic setup of a t-table. Okay, it's not a bad setup. Sometimes it could be better choices, but in this case, this will work. Okay, so this is 2 to the 0. What is that? It's 1. So this value here, x is 0, y is 1. Right? 2 to the 1, right? 2 to the 1 is equal to 2. 2 squared, that's 4. So we have a 4 here. And 2 cubed, right? That's the interim sum. That's 2 times 2 times 2. That's 4 times 2 is 8. Right? 2 to the -1, that's the reciprocal. So that's half. And 2 to the -2, that is -4. Or I'm sorry, but it's not, it is 1/4, positive. Okay. So we could go ahead and graph this. Okay. Now, in the inverse function, remember what we're doing, right? So x's become y's, the y's become x's. So in f inverse, these are your x's, and those are your y's. All right, I'm just going to redraw it because it's easier to think that way. But when you want to draw, like if you were asked to draw out the logarithm, like we're going to do in the first example here, since it's an inverse function, right? So if I want to do, okay, what is log base 2 of x? This is equal to y. If I want to graph this, what I'm going to do is I'm going to pick my y's first because it's the inverse. So what's a good choice for a t-table, right? Now we do -2, -1, 0, 1, 2, 3. Right? Now, we also have something called equivalent exponential form. What was the base? It's 2. Then 2 to the y is equal to x. Okay. This is you're gonna have to remember this, but it's hard to remember. Like it's like this weird circle loopy thing. Back when I was in elementary school, I was not the astute student in math. Okay, they sent me out to the hall, and I had to work with a tutor with flashcards to learn my arithmetic stuff and my times tables. But it was Catholic school, and they had one set of flashcards. Well, they had several sets, but they had one standard set. And this school went up to 8th grade, so they had square root flashcards. Okay, for the 6th, 7th, 8th graders. Okay, not for 2nd grade. Catholic school is nice, but not nice. But they also had logarithms, and I remember seeing these, and I remember asking, like, "Ooh, what's that?" I said, "That's an exponent." And to a 2nd grader, that is a useless answer. But time to get back to work. But I've asked other people, like later in life, and it's what's a logarithm? Say it's an exponent. The answer you get, like log base 2 of 32, what's the answer? Well, what we're doing is we're saying 2 to what power is equal to 32? 2 to what power is equal to 32? Again, go back to your intro song, and after you've sung the song 5 times, you get 32. So that's what the answer is, right? The answer value is, what's a logarithm? Well, the answer is going to be the exponent. Okay, so now you can be as horrible and as obnoxious as everybody that I've ever asked. Somebody asks you what a logarithm is, it's an exponent, because that's what the answer is. It's what you raise the base to in order to get to the argument. So this guy here, this is the base, and this one here is the argument. Okay, so 2 raised to the 5th power is equal to 32. So when I'm looking at this, right, the answer is going to be, well, how about we try this one? 2 raised to what power is equal to, or 2 raised to the 0, right, is equal to what? 2 raised to the 0 is 1. So we put a 1 here. 2 raised to the 1 is equal to 2. So we put a 2 here. 2 squared is equal to 4. And 2 cubed is equal to 8. Okay, so what I'm trying to do for us, right, is you're going to be using this form pretty much to fill in this table. So if you're ever asked to graph a logarithm without a calculator, without a computer, you're going to go to your equivalent exponential form, and you're going to say, oh, that's right, logarithms are inverses. I got to think about them backwards. Let's fill in the y's first, and then figure out what x's we need in order to get those y's. Okay, so you're looking, that's an eye, or satellite, okay, because satellites are cameras, but that's an eye. You're looking at the y's first, okay, so just want you to realize that the y's are the things that come first, and then we sort through the x's. 2 to the -1, 1/2, and 2 to the -2, 1/4. Okay, now we can graph, but we have it in the right order, so when we are thinking about like how to graph stuff, we're going to be okay, right? Other thing we know about logarithms, let's go all the way back up here. Logarithm is an inverse function of the exponential. So what is the domain of a logarithm? What's the domain? It's the opposite, right? So the range here was 0 to infinity. So the domain in the inverse, right, is the original function's range. How about the range? Right, and that's going to be -infinity to +infinity, because the domain of the exponential, right, is this. And then remember we had an asymptote at y equals 0. We had a horizontal asymptote at y equals 0. When we flip it and we look at the inverse function, we're going to have a vertical asymptote at x equals 0. All right. So let's go ahead and graph this thing. Looking at my domain though, it's just positive numbers. So if I want to draw a domain, I don't need any negative x's, do I? So here's what I'm interested in. Okay. So we have to go out to x equals 8. Okay, about half of that is x, pretend that's half. Okay. Then we have half again is 2, half again is 1, half again is a half again is a quarter. 1, 2, 1, 2, -1, -2. All right. So when x was a quarter, y was -2. So we're going to put a dot here. Okay. When x was a half, so there's a half, we're going to go down here. When x was 1, that's a thing. When x is 1, y is always 0. Okay, for every logarithm. Okay. When x was 2, y was 1. 4, we're at 2. And 8, we're going to be at 3. Okay, pretend there's a 3 up here. Right? So here is our graph. Okay. The other thing about Catholic school is that I never thought I was going to do very well because I couldn't color inner lines or fold or tape or anything. So the fact that I can't connect the dots today is, well, that's going back to kindergarten. Okay. So that, and by the way, if I ask you to graph it, your graph looks half as good as mine, you're set. All right. So there is how to graph a logarithm. Right. So start with the y's and then use the equivalent exponential form. We have y is equal to log base b of x. This is the same as b raised to the y is equal to x. This is one of those things that you should know. Right? It will come up because I will ask you to graph a weird log. Okay? But to be honest, I'm glad your book actually does a good job with this. My algebra book spent like sections dealing with logarithms that weren't normal ones, because this is kind of a fiction. Okay, you really only deal with 3 logarithms. Okay, this one's rare. This is the button on your calculator, right? log on the button on your calculator, ln the button on your calculator, lg the button on your calculator. This is really log base 10. This ln, not n. Okay, ln, L as in that one. Okay, this is the natural log. This is log base e. Okay, and lg, this is computer science people. This is log base 2. Okay? So these are the logs, like when you like log of 1/5, like that, it's not happening. All right, it's neat to look at. That's the base of 1/5. But if you're looking at this problem, you're like, I just never got this. Like, you'll live. Okay, you'll be just fine. You'll get the one problem wrong on your exam. Okay, but you'll finish the course. You'll go on to do great things. It won't matter. Okay, but if you don't ever understand, like, what do we do with the different bases? It's these are the 3 you care about. Okay, so if you like, I have mastered natural log, but log base 1/5 is completely baffling. You'll be fine. Okay, what do we need them for? What do we use a log for? We use them to write down things that are really, really, really far apart. Okay, so logs are used to display large differences in numbers. Okay, what if you're a biologist and you're studying sizes of viruses? Okay, and you're just looking at like maybe you have a theory about you want the size of an organism and you want the doublet time. Okay, we'll make a better thing here. Okay, so now I don't know how big these things are. I probably should have researched this on Google. researched. I should have looked this up on Google before I went and came up with an example here. But what if I wanted to get the size of a virus? Okay, and we're not talking nanometers, right? We're probably talking micrometers here. Okay, so maybe viruses, you have a couple of viruses on here, and they range from, say, 60 micrometers to, let's go to 500 micrometers. Okay. And you do some bacteria. And bacteria, we're going to go with millimeters. Okay. Now, they're probably micrometers too, but what if we go for like 0.9 millimeters in size up to like 2 millimeters? Okay. That's a really big bacteria. I'm sorry. Is anybody's an actual biologist here? You're watching this, please forgive me. I have no idea what I'm talking about. Okay, and we have maybe some other things here. All right. So we already can see like this is 1,000 times bigger than this. I want to draw this graph of like going like, well, here's 60 micrometers, 120, 180, 240, and then having to crawl all the way up to 1,000 and then graph this. Oh no, we don't want to do that. So what we're going to do is we're going to take logarithms of these numbers, and that's how we're going to do it. Wait, let me give you something that I at least have some working idea of. About every year or for something, we talk about the budget of the United States, and we have big fights about it. And we have things that cost millions of dollars. Okay, and if you look at the metric system, scientific notation, right? We have times 10 to the 6. This is a million. Okay, billion. This is times 10 to the 9th. We're using the USA system here. The English have a different way of counting millions and billions and trillions, which make much bigger numbers. But the USA standard is like what banks around the world use, so we'll use the USA standard. Besides, most of my students live in the USA, so. And times 10 to the 12th, that is trillion. Okay. Now notice there is a million millions in a trillion. Okay. Just want you to realize there are a million millions in a trillion. Okay. Because if you have something you have to do here, right, you're going to multiply it out. Let me give you something that you probably have more familiarity with. Okay. Times 10 to the 3, this is 1,000, right? We use that for a K. Times 10 to the 6, that was million, we use M. Times 10 to the 9th, well, this is in metric, right? This is giga. This is mega. This is K, thousands. K kilo. Right? And times 10 to the 12th is tera. You have hard drives now that have times 10 to the 12th bytes in them. We probably have giga drives, right? Gigabyte drives, gigabyte speeds. Back when I was growing up, we had our 512 kilobyte drives, okay? You look at that now, you're like, I don't even notice, right? And then when I got to college, I'm like, ooh, technology improved. We have megabyte drives. I'll never fill this up, right? So you're looking at like, we have 256 megabyte drive. That's huge. Now you guys have like 512 gigabyte drives, right? And some of you probably have terabyte to keep some stuff on. You have a gigabyte drive, let's just say, for example, or you have a terabyte drive, let's just say, for example, you have a terabyte hard drive, and you're just having a bunch of music on there. Do you even see these? Okay, do you even recognize that there are megabyte files, megabyte sized files on your terabyte hard drive? Okay, you don't even see it. Even on your gigabyte stuff, right? You're looking through like, oh, I gotta make some room. Like, what are you looking for? You're looking for gigabyte stuff to make room. You don't care about this. Maybe a little bit. I mean, if it's like, really big, it's close to a meg, or close to a gig rather, you might care, right? So if it's like 0.9 gig, 900 meg, then you might care about that file to get rid of it, to make some room. Okay. I can't even remember the last time I had to go through my hard drive and clean it off in order to make room. Okay. Because we're looking at here. So again, you've got a terabyte drive. Do you even notice this? So here is our trillions of dollars, right? Or no, not trillions, I think. Yeah, here we are with our trillions of dollars. Do we even see a million? Not even close. You don't even see it. So it bugs me when I hear people talk about, like, we're spending trillions of dollars. No, we can't have that project. That costs millions. Like, you have a terabyte drive and you're going to get rid of files because they happen to be a couple more meg. Like, you don't care. But we're going to put this on a graph, right? We're going to put all of our spending projects on a graph. Right? I don't know what our y-axis would be. Like number of utility. We'll come up with something that we're going to measure in utility. No idea what that would be. We're going to measure it. Do you really want to go through the billions? And then after you get to 1,000 million, you're at a gate, you're at a billion, and you're going to do that for 1,000 little ticks. And after 1,000 little ticks, you're going to go up to a trillion. No, you're not doing that. So wouldn't it be easier to say, here's my thousands, here's my millions, here's my billions, here's my trillions. Because log base 10, all you do is count the zeros. Okay, so log of 10, that's 1. Log of 100, what is it asking? 10 raised to what power is equal to 100? It's 2. Log of 1,000, 10 raised to what power is equal to 1,000? It's 3. So all we do is count the zeros. Since I know that in $1 trillion, there's 12 zeros, 12 places, that's it. There's our graph. Okay, this is a lot easier to deal with. That's why you would want to deal with a logarithm. Okay, so they really, all the stuff that we teach you is like, this is supposed to make your life easier, not harder, right? So I'm going to stop this video here as like my intro to logarithms, or at least so you have the idea. And then we're going to go on to do some other problems in a moment. Okay, so we're going to stop and I'll do some more. Okay, thank you. Good luck with doing homework.